Okay, so I'm just gonna record a quick video about z-scores. So I think everybody was in school for z-scores, but if there's anything you missed, then this is the video for you. So this is just basically what we did in class for z-scores. So if we went too fast and you felt like you got left behind or you missed something, then here's another explanation of it. Z-scores are probably, of the statistics things, z-scores are more important than standard deviation and things like that, but about as important as lines of best fit and the inverse variation, okay? So let's talk about z-scores again. Okay, so we have this data set here, alright, and these are the heights in inches of some high school basketball team members. And the first thing that we're asked to do on this z-score worksheet, so this is exactly what your z-score worksheet looks like. We're going to find the mean and the standard deviation. So as a quick recap of how to do that, that's just, we get out our calculator, okay, and we're going to make a new document and do a list and spreadsheet, okay. So we're just going to name it. Remember, we're in that habit. It's really good to name it. It's been great seeing you guys kind of pick that up and not have any issues with that, okay. So let me write this down really fast. And now I can go ahead and type these into the calculator really fast. So I'm just putting them in. And now, right now, we only have one variable, right? The only data we have is the heights of the basketball team members. We don't have the heights of the basketball team members versus the shoe size that they wear or the number of baskets that they score. It's only the heights of the basketball team, right? So it's just one variable. We only need our x in this situation. There's no y. All right, so I'm just typing in these heights, which if you're following along on your notes page, you can see them at the top there. I have them written down in front of me, so I'm just typing them into my calculator. Okay, and again, I recommend getting a calculator. Seriously, it'll help you so much for the rest of high school and then the rest of college if you have a really good graphing calculator that you are able to use often and master. You know, you don't get hung up on how do I do that on the calculator again. You always have your calculator as a backup and to help you solve problems. So I'm almost done here. Alright, so now that I'm done, now note I pushed enter on the last dot, or the last data point, and now my box is still in the first column. And these are two very critically important things if you want your calculator to do what you want it to do. In our case, we want it to find one variable statistics, okay? So that means it's going to find things like our mean and our standard deviation for us. So we push menu and statistics, and then statistics, and then stat calculations, and one variable statistics, right? That's exactly what we want. We're just going to push OK. And now it looks like, oh no, where did all my statistics go? But remember, we just need to scroll up in order to get to all of those, right? So the very first thing it asks us for is the mean, and this right here is our mean. So our mean is 71.375, and for our purposes today, we're just going to write that down to 71.4. Okay. Just a little bit easier to deal with the decimals if we do it that way. Okay, so let's look back at our worksheet. We'll type that in, 71.4. Okay, and then the standard deviation. Remember, standard deviation is our little dude with a hat on. Okay, so we're going to look at our calculator here, and we're going to scroll down until we see that, oh, there's our little guy with a hat on. Okay, so that means 2.89 is our standard deviation, which means we can go ahead and round that to 2.9. Again, just to make our calculations a tiny bit easier, okay, so 2.9. Okay, so what I want to do, I'm going to go ahead and I'm going to put this on a number line. So I put it on this number line, and I'll use little stars for our data points just to make it pretty. But this is going to be really helpful for us because now we can kind of see what all these statistics mean, right? So the mean is our balance point for the data, and so I'm going to go ahead and use a nice blue line here to show the mean on here. So here's 71, so it's going to be a little less than halfway between 71 and 72. So there's our mean, okay? And then our standard deviation is what is the average distance that each point is from the mean, okay? So what we're going to do is we're going to draw on the standard deviations, okay? So 71.4 plus 2.9. And this is just kind of to show what, you know, these things mean for us here. So we have, I'm going to go to the scratch pad. We have 71.4 plus 2.9. So 74.3 All right, so that's 74.3. So 74 point, and I'll use green for this first one standard deviation away. All right, 74.3. Now we want to go another standard deviation below the mean, right? Because a standard deviation can be above or below the mean. It's just the distance from that mean, okay? So we'll go one standard deviation below the mean now by doing 71.4 minus 2.9, which gives 68.5. Okay, so 68.5. Alright, so there's one standard deviation. So that means that between the green line and the blue line is 2.9. It's 2.9. Okay, so that's one standard deviation. So I'll go ahead and write that on. So this is here, this is 2.9. One little guy with a hat on. Right, and then between this blue line and this green line, we have 2.9. So this is one standard deviation. Okay, so now let's go one more standard deviation away. Okay, just for funsies. So another 2.9 from 74.3. So that's going to give us 2, carry the 1, 5 plus 2, 7. Alright, so 77.2. Alright, 76, 77 point, and let's go ahead and do this one in orange. How about that? So 77.2. Alright, and below the mean we have 68.5 minus 2.9. And we go ahead and erase this in a second. So, alright, so that's 17, 15 minus 9 is 4, 7 minus 2 is 5. 65.4, okay. Alrighty, so now we have a second standard deviation on there. There you go. Okay, so let me write that in there. Okay, so now between the green line and the orange line is another standard deviation. Okay, it's another guy with a hat on. Same up here. Alright, but between the orange lines and the blue line is 2 standard deviations, right? So I'm going to go ahead, let me just cover up some of these words that I don't care about right now. Okay, I don't care about those, so I can cover those up all I want. So I'm going to do this. That's 2 standard deviations, that's highlighted in blue. And then 2 standard deviations that's highlighted in blue, okay? So, so that's just going to be a visual, and that's going to help us in a second, to help us understand what's going on here, alright? So anyway, so now it asks us how many elements are above the mean. And this is really easy because since we put it all on a number line, we just look for blue, which is our mean, and we can count how many things are above it. So how many things are bigger than the mean. Okay, so that's 1, 2, 3, 4, 5, 6, 7, and 8. 8 things are above the mean, okay? And if we wanted to do this without putting it on a number line, we would have just said, well, my mean is 71.4, so how many things in the data set are bigger than 71.4? Here's 1, that's not bigger, that's not bigger, that's not bigger. 2, 3, 4, not bigger. 5, not bigger. 6, not bigger. 7, not bigger, not bigger. 8, so that's 8 things, okay? And then how many things are below? Well, anything that's less than 71.4, so that's 1, 2, 3, 4, 5, 6, 7, and 8, okay? Or we can count that on the number line. 1, 2, 3, 4, 5, 6, 7, 8. So how many things are above the mean? 8. How many things are below the mean? 8, okay? So how many elements are within 1 standard deviation of the mean? Okay, so now within 1 standard deviation is basically we're going to look at how many things fall between the green line and the blue line on either side. Okay, so what that means is these things that are within 1 standard deviation mean that they are either 1 standard deviation less than the mean or 1 standard deviation bigger than the mean. Okay, so I believe our upper bound that we had here was like 74.3, and then this down here was 68.5. Okay, so if we go ahead and count, right, all we need are the things that are with it between this green line, this blue line, and then this blue line, that green line. Okay, because this is 1 standard deviation, this is 1 standard deviation. So within 1 standard deviation, the mean means you're basically saying, like it's like saying how many people are within 2.9 inches of the mean, right? That's our standard deviation. So within 2.9 inches, that means if I am only 2 inches smaller than the mean, then that means that I am within 2.9 inches of the mean. Or if I'm 2 inches taller than the mean, I'm still within 2.9 inches. So it makes this little bubble of values around the mean that we want to count how many things are in there, okay? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 things, okay? So all I did was create this little like range, and then I could count those things, all right? The other thing I could do is look for things that are bigger than 68.5, okay? Remember that's 71.4 plus 2.9 gives me 74.3, and then 71.4 minus 2.9 gave me 68.5, okay? So I'm looking for things that are either bigger than 68.5 or less than 74.3, and that would be, this would be in there. I'll go ahead and use red for this. All right, that's in there. That's not, that is, that is, that is, that is, that is, that's not, that is, not, is, okay? So, I don't really need to explain that on paper because I just explained it using the video, okay? So now what percent of the data is more than one standard deviation above the mean? So more than, okay, that's going to be anything that is bigger than this upper green line, okay? So that's, we see we have one thing and two things that are bigger than that, okay? So it asks for a percent, so we need to make sure we're careful about reading it. So it's 2 things out of 16 total things in the data set. Gives me 1/8 of the data, which if we were to convert that to a decimal, that would be 12.5%, because that's equal to 0.125, and then turn it into a percent, so 12.5%. Okay? Now, how many standard deviations from the mean is the player with a height of 67 inches? Okay? Now, in class, I explained this kind of like this. All right? So, imagine for a second that I have, let me put in a page. All right, I have 6 apples. So 1, 2, 3, 4, 5, 6. And these apples are in a bucket just individually. And I say, I'm going to give 1 apple to as many people as I can. So how many people can I give them to? Well, that's 1, 2, 3, 4, 5, 6 people. Okay? Now, let's say again that I have these same 6 apples. Okay? But ahead of time, I went ahead and put them into, groups of 2. Okay, and now I say, how many people can I give, apples to? Then that's going to change into 1, 2, 3 people, right? So the operation that we're doing each time is we're doing 6 divided by the size of my groups, right? 6 divided by the size of my groups, right? Or, if I have 6 apples and, I've broken it ahead of time into groups of 3. Well, now I can give it only to 2 people. Give 3 apples to 2 people each, okay? So 6 divided by the size of my groups equals the number of number of people who get apples, okay? All right. Now we're going to do the same thing with standard deviations, okay? So pretend for a second that we're saying that I want to know how many standard deviations away from something something is, okay? So let's go back to our page here. All right, so how many standard deviations from the mean is the player with a height of 67 inches, okay? So if we look on the number line, we find 67. There's 67, okay? We know it's going to be more than one standard deviation because there's our first deviation, okay? And it's going to be somewhere around the middle of that second standard deviation, okay? Well, we want to know exactly how many sets of 2.9 do we have to go in order to hit 67. Okay, so if you look, there's a few different moving parts that are happening here. All right. So before we even think about chunking it up into standard deviations, if we want to know how far 67 is from the mean, right, and then break that up into chunks of standard deviations, we have to start with finding how far from the mean is 67. All right, and so that, when we're talking about how far, the distance, the difference, or the deviation, what we're really talking about is doing 67 minus the mean, which in this case is 71.4, okay? So this gives me my deviation, or the distance from the mean, which is equal to 60. It's just faster to do it this way. Alright, gives me negative 4.4. Okay. That's not what I wanted. Okay, which gives me negative 4.4. Alright, so that means the deviation, the distance from the mean, is negative 4.4. So looking at that number, right, we have 4.4 units below, right? So that negative, we know that 67 is smaller than 71.4, so that negative means that it's sitting below, that's below the mean. We know that it's negative 4.4 that we have to work with, and we want to know how many standard deviations is that. Okay? I know that it's 4.4 away from the mean, but how many standard deviations is that? So if we do, what we're asking now is, let's pretend that 4.4 is apples again. Alright, so we have 4.4 apples. And I want to chunk it up into groups of 2.9. So how many people can I give apples to? Okay? So if we look back at the other illustration we were looking at, if I have 4.4, well, negative 4.4 apples, obviously we can't have negative 4.4. Let's pretend that we can. Okay, we have negative 4.4 apples, right? Because up here, this was our apples, total apples. Alright, and then I'm saying I want to chunk it up into groups that are of size 2.9, right? And we want to do that because we're asking how many standard deviations, how many of these chunks can we fit in between there, okay? So my group size is 2.9 because for this data set, the standard deviation is 2.9. So your standard deviation and your mean are going to be different for every single data set that you work with, and the deviation from the mean is going to be different for every data point unless it's a repeated data point. So this is a process that we would have to repeat multiple times if we wanted to look at both 67 and 72 and 74. We're not going to have just one number for the number of standard deviations. 74 is from the mean and 72 is from the mean and such. We're going to have to do this over and over and over to do that, okay? But so let's go back to this illustration. We have negative 4.4 apples, and the size of my groups in this case is 2.9, okay? So we're dividing. And what that's going to tell us is if I have 4.4 apples and they're grouped into 2.9, how many people can I give it to? Well, that's going to be negative 1.52 about, okay? Right, negative 1.5. Oopsie. A little laggy there. 1.52. Alright, so what that's telling us is that we obviously can't have negative 1.52 people, but what it is telling us is that we've now broken our deviation of negative 4.4 up into chunks of standard deviations, which are size 2.9, and that means that there are negative 1.52 chunks of 2.9 that fit in here, okay? So let's look back at this. Let's scroll back up to this number line, right? I'm going to go ahead and make a line, a fat line here, that represents, let's make it purple, light purple, okay? That represents the size of this standard deviation, okay? And I'm going to make it somewhere where I will be able to move it. All right, so here's my fat line. This is one standard deviation, okay? And now I'm going to copy this line, okay? I'm going to say, all right, so I have two of them, okay? So I want to say how many standard deviations, how many chunks of 2.9 does it take to hit 67? So I put my first one on my graph here, and there's 1. Okay, so I know it's 1. And I see that 67 is below the mean, so it's obviously going to be a negative number that go in here, okay? And now let's say I need to get to 67. Well, now we've overshot 67, right? So let's break this up a little bit more then. Now let's make it yellow. Okay. I don't want half of this, right? Because 67 is right here. So that's about half of it. And when I do about half of it, that gives me about this 1.52 number that we have, okay? So we took one standard deviation away from the mean and then part of another standard deviation away from the mean. And it's about half of that second standard deviation away from the mean. Okay, so to finish out these notes down here, what we would have is this negative 4.4 divided by 2.9, which gives me negative 1.52. Okay? So what we just found, when we find that number of standard deviations away from the mean that a number is, that's called the z-score, okay, the z-score. So a z-score, also called, that's not on your notes, and we're not going to do it, okay. Oops, I do want this first part. We don't want this part. No, I'll do this. It's cleaner. Okay, a z-score. A z-score is a measure of dispersion, again, okay? These are all measures of dispersion, okay? A measure of dispersion, because the z-score, well, it's not necessarily a measure of dispersion. A z-score is a measure of the distance from the mean. So it's kind of like dispersion, because it's like bigger z-scores. If you have a bunch of elements with big z-scores, then, well, no, it's not a measure of dispersion. It's a measure of the distance from the mean for each element, okay? For each. Okay? But since the mean and the standard deviation already talk about the dispersion, like the mean talks about the central tendency, and the dispersion talks about the standard deviation talks about the dispersion, the z-score is kind of this standardized way to talk about elements and how they relate to the rest of the data set and relate to the mean, okay? So it's the measure of the distance from the mean for each element, okay? I'm just going to erase this word dispersion up here, all right? So it is derived from the mean, okay, which is a central tendency measure, and the standard deviation. Okay? So we use the z-score to determine how many standard deviations, okay, and I'm just going to start writing the guy with the hat, okay? How many standard deviations an element is above or below the mean of the data set, okay? So, some characteristics of z-scores. It tells how many standard deviations an element is above or below the mean, okay? I'll just write it in. And it's going to be positive if an element lies above the mean, okay? So that shouldn't be super mysterious to us, right? 67 was shorter. Oopsie, went too far up there. 67 was smaller, right? If you're 67 inches, you're shorter than the 71.4 inch mean. So that's below, it's below the data set to the left of the mean, okay? And so it had a negative z-score, okay? It's, with that negative z-score saying you're 2.9, or your 1.52 standard deviations shorter than the mean, okay? So if they're positive, that means you're 2.9 or you're 1.5 deviations, standard deviations taller than the mean, okay? So if it's negative, that means it lies below the mean, okay? And where that comes from is up here we did, if we were to write it all at once, 67 minus 7.4 divided by 2.9, right? So if it's below the mean, you're going to have a number that's smaller than the mean minus the bigger mean, which gives us a negative number, divided by 2.9, gives us a negative z-score, okay? But if that number is, say it's 78, right, the biggest element in our data set, if you do 78 minus 71.4, that's going to give you a positive number. So a positive number divided by a positive standard deviation gives us a positive z-score, which means it's above the mean, okay? So that is calculated by subtracting the mean from the element and then dividing that result by the standard deviation. Of the data set, okay? So we look at this, x is an element of the data set, okay? This funky mu, which shows up in your calculator as this little symbol, okay, is the mean, okay? And the guy with a hat on, who also shows up in your calculator like this, is the standard deviation. okay? So using the formula above to calculate the z-scores for heights of 69, calculate those z-scores for 69 inches and 78 inches, okay? Are you ready for how simple this is? All right, we know right now, we know our standard deviation is 2.9, and we know that the mean is 71.4. So our formula is x minus the mean, data element minus the mean, divided by standard deviation, okay? So let's plug things in. First, let's do it for 69. Okay, so 69 minus 71.4 divided by 2.9. And that gives us 69 minus 71.4 divided by 2.9. That gives us negative 0.828, so we'll just round that to negative 0.83. All right. So for z-scores, you can pretty much count on just going to the nearest hundreds, okay? So negative 0.83. So that means you are 0.83 standard deviations shorter than the mean if you are 69 inches, okay? For 78 inches, we have 78 is the data element, the mean is 71.4, and the standard deviation is 2.9. So if we plug that into the calculator, we get 78 minus 71.4. And if we divide that by 2.9, we get our z-score, which we're going to round to 2.23. Okay, so 78-inch tall guy, super, super, super tall compared to the rest of the team. In fact, he's almost 3 standard deviations taller than the average height on the team. Okay, so probably gets his dunks on, right? So 2.23 above. All right, so look at the data set. How many z-scores are going to be positive? Well, that's every single number that's bigger than the mean is going to have a positive z-score, right? If it has a positive z-score, it's above the mean. And we've already done this. We did up here. How many things? Dang it. How many things are above the mean? How many elements are above the mean? Those are all going to have positive z-scores, okay? No, we said there were 8. How many are below the mean? They're all going to have negative z-scores, and we said there were also 8. So we can go on down here and say how many would be positive? 8 we're going to be positive, and how many are going to be negative? 8, because there's 8 above the mean, 8 above mean, and 8 below mean. Okay, so now suppose that you know a data element has a z-score of 1.25. Okay, so let's write out what we know just as it introduces information. Okay, so the z-score is 1.25, and it wants us to find the data element, so we don't know x. And we want to know if that data element exists in our list of heights, okay? So we also know the standard deviation is 2.9, and we know that the mean is 71.4, okay? And we know that z is equal to x minus the mean over the standard deviation. So now let's just plug junk in, right? So we have 1.25 is equal to x minus the mean, so we don't know x. But we do know the mean, 71.4, and divide by 2.9. So to find this data element, here we go. You ready? So we're going to do 1.25 times 2.9. This gives us 3.625. Okay, so 3.625. So our first step was to multiply by 2.9 on both sides, because over here, this is all divided by 2.9. So we just did this, 2.9, 2.9. Okay, so 3.625 is equal to x minus 71.4, and now in order to get x alone, we're going to have to add 71.4 to both sides. And so plus 71.4, and that gives us 75.025, okay? So 75.025, and so if you are 75.025 inches tall, okay, or about 75 inches, then you are 1.25 standard deviations above the mean, okay? So it asks, is that element in our list of data? I went too far again. Here's 75. Yes, it is. Okay, there's 75. It is. So then that will be our answer there. Okay. All right, so there's z-scores. I'm going to post another video that has the answers the explanations to the rest of the z-score sheet, then I'll do one for standard deviation, and I'll do one for mean absolute deviation, okay? So go ahead and check those out if you want to watch those. I hope z-scores are making more sense to you now. Alright? Sweet.